All right, what we're going to look at now is how we can use mass percentages to find the empirical formula of a compound. Now, we just did a lab a little bit ago in which we experimentally determined the empirical formula of a compound, but just to review, an empirical formula is a formula of a compound reduced to its lowest whole numbers. So, for example, the compound hydrogen peroxide has a formula H2O2. That's its molecular formula. But notice if I divide both of those subscripts by 2, I get a simplified formula. This is the empirical formula. Or, for example, um, benzene. Benzene is C6H6. If I divide both of those numbers by 6, the empirical formula is CH. Now that's CH doesn't exist as a compound, but that's the empirical formula for the molecular formula. Or like P4H10. Um, I can't divide them both by 4 because I wouldn't get a whole number for hydrogen, but I can divide them both by 2 and get to P2O5 as the empirical formula. Now, the way I'm going to get there to the empirical formula is using technology. We have technology that can find the mass and or percent mass. I'll use it properly, mass percent of each element in a compound. So a lot of times in a problem involving finding an empirical formula, um, well, we have the technology to find either the masses of each atom or the mass percent. So for example, so a sample of a compound was found to contain 60% carbon, 4.48% hydrogen, and 35.53% oxygen. What is the empirical formula of the compound? Now, in problems like this, you'll either be given mass percent or you'll be given the masses. So if you're given mass percent, there's just one little extra step at the beginning. Step one is to change all the percentages to grams. And the easiest way to do this is just assume you have 100 grams of that element. Because if this thing is 60% carbon and I have 100 grams, that's 60 grams of carbon. If it's 4.48% hydrogen and I have 100 grams of it, that's 4.48 grams of hydrogen. I'm just multiplying all these percents by 100. Or in reality, if all you want to do is just kind of drop the percent and make grams, that's fine. Just whatever you want to do to kind of keep it straight. But I'm basically just taking those percentages and making them into grams first. Now, the second step is to convert all those grams into moles. How do you do that? What number do you need in order to go from grams to moles? We need the molar mass from the periodic table. 60 grams of carbon has a molar mass of 12.001 grams in 1 mole. So grams of carbon cancel out. And I have that many moles of carbon. I'll do the same thing for hydrogen. Again, I'm going to look on the periodic table and pull that number off of the periodic table, 1.008 grams of hydrogen. And I have 4.44 moles of hydrogen. And I'll do this one more time for oxygen. So the molar mass is 15.999 grams of oxygen in 1 mole of oxygen. And that's step 2. Step 3, I'm going to take each of those mole values I just calculated in 2. So put each mole value over the smallest mole value. So for this list, it's oxygen. And so I'm going to do this for each element. So for carbon, it looks like this. 4.995 over 2.221. I don't care about units with this. I'm just looking at a ratio. And for hydrogen, that's 4.44 over 2.221. And for oxygen, that's, well, it's the same thing over each other. And I'm going to calculate these. So I get 2.25, 2, and 1. Now, step 4 is put the ratios you just calculated in step 3 in a formula. Like, but that's going to look kind of weird. Yeah, exactly. It's going to look like that. It's going to look weird for a minute, and then we're going to fix it. So carbon we have is 2.25. Hydrogen was 2, and oxygen was 1. Now, I'm not done. That's not the empirical formula. I need to multiply this by a certain number to make it a whole number. Remember, I can't have half an atom or a quarter of an atom in a molecular formula. It's got to be a whole number. So what do you think I can multiply that 2.25 by to make it a whole number? I'm going to multiply this by 4 to make it a whole number. But here's the catch. What I do to one subscript I have to do to all subscripts. So I'm going to take all of these, multiply them by 4. And so for carbon, that comes out to 9. For hydrogen, that comes out to 8. And for oxygen, that comes out to 4. Now, this is our final answer. This is the empirical formula for this compound. It may turn out to be also be the molecular formula, or it could be C18H16O8, or it could be C27H24O12, and so on. We don't know until we get a little bit more information. In the next lecture, what we're going to talk about is how, once we know the empirical formula, if we know some other information, we can convert that to the molecular formula. So that'll be in the next lecture, but I want to do one more example before I stop this one. So what happens if I'm not given mass percent? What if I'm given the actual masses of the elements? Well, this kind of makes it a little bit easier. Because if we're given the actual masses, we don't need to do any percentage stuff. So we can just go straight from grams to moles. So in this problem, the mineral hematite was found to contain 34.97 grams of iron and 15.03 grams of oxygen. So we can kind of skip over the whole percent thing. We already have grams. So we're just going to go from grams to moles. So I'm going to look up on the periodic table and get my molar mass. So that's 0.6303 moles of iron. I'll do the same thing for oxygen. Again, I'm getting this information right from the periodic table. Hopefully this should, be second nature to you. You go right to your periodic table. And that comes out to 0.9394 moles of oxygen. And then I'm going to do the same thing I did before. Okay, so put each mole over the smallest mole. So for iron, that looks like this. And that comes out to 1.49. And for oxygen, it's just going to be 1. Did I mix up my values? I did. I'm so sorry. I mixed up my values. This should be oxygen, and this should be iron. Sorry about that. Okay, now I'm going to take those and put them in a formula. So Fe1, oxygen 1.49. Now, here's what I'm going to do. That 1.49 is really, really, really close to 1.5. In fact, if I rounded it a little bit more, I get to 1.5. Now, why am I making this assumption? Because it makes the next math a lot easier. Because I can multiply this by 2 to get to a whole number. But again, what I do to 1, I have to do to both of them. So I'm going to multiply both of these exponents times 2. I'm not exponents, but subscripts. And so that comes to Fe2O3. And that's my final answer. All right, in the next lecture, we're going to take a look at how we can combine this with just a little bit more information, and we can get to the molecular formula from the empirical formula.